Now, we've all heard about these new coronavirus vaccines that have been developed and have begun to be administered around the world. And it's an incredible feat of science and medicine. However, I'm sure all of us have probably also heard about how there might be some side effects from the vaccines that we should be prepared to experience. However, sometimes side effects can sound really scary because that's like that list of doom that you hear on the TV commercials that usually starts at unpleasant and ends in really bad. Is this what we're talking about? The good thing is that no. As the follow-up usually is to these statements, these side effects are evidence that your immune system is working and that you'll have a pretty good protective response to these vaccines. But if you're still a little unsure about how this makes you feel, or you just want to understand what that means, that side effects mean the vaccine is working, you've come to the right place. Hi, I'm the Geeky Goth, and today we are going to be scratching the surface of the immune system so that we can answer this question: how do vaccines work? If you were to ask an immunologist, their answer will probably start with something like, well, it's complicated. And it is complicated. But today, we're going to look at one of the key tools that the immune system uses so that we can understand a little bit better what these side effects are and why we might experience them in the first place. Consider for a moment the most commonly reported side effects to these vaccines. Those are fever, injection site pain, chills, body aches, and fatigue. None of these seem very terrible, but why might we experience these in the first place? Let's start by looking at what our immune system does in response to these vaccines. Alright, now once our cells have made this viral spike protein and they've stuck it out on their surface like a lawn ornament, our immune cells are going to see it as something that is not self. Now, not self just simply means that this is a protein or other molecule that the immune system sees, but that it hasn't been told belongs. And anything that the immune system isn't told belongs here must be an enemy. It's just how it works. Now, normally at this point, you start to see all of these little antibodies come into the picture. But the issue with this is that we don't make antibodies instantly. It's not like instant antibody. So instead, what this first immune cell is going to do is it's going to sound an alarm. It's going to alert other cells that there is something here that doesn't belong. Of course, cells can't talk or wave any sort of a red flag, so they have to communicate in another way. And the way that cells do this is with the use of molecules. But these molecules come in a variety of classifications with a plethora of functions. Some of these are responsible for raising our body temperature, others for dilating our blood vessels. Many will help to recruit and then lead more immune cells to this site. And then there are more that have several other functions that we're probably familiar with, from causing us to itch or cough or sneeze or just to make our noses snotty. Now, before we get more into the functions of these molecules, let's look at that tool that the immune system uses. I'm certain that we've all heard this word before: inflammation. You can sit and think about what it means to you, and you're probably going to describe the very criteria I'm about to mention. Inflammation isn't so much a thing as it is a description or a collection of things. Inflammation can be described by 4 main criteria: fever or heat, pain, redness, and finally, swelling. Now, you probably recognize and have even experienced at least one, if not all of these at some point. But what do they have to do with an immune response? Well, because we probably already recognize fever from our list of side effects, let's start there. When something unfamiliar enters our body, it's going to take our immune system a little bit of time to respond. Now, if this threat is a living organism, something like a bacteria, a fungi, or maybe a virus, then in this time period of the immune system responding, at our normal body temperature, these organisms are going to continue to grow. They're going to replicate, because the whole reason they infect us is because they like our body conditions. But this means that by the time our immune system has activated and gotten onto the scene, things are already out of control. However, by raising our body temperature a few degrees, this makes our bodies a much less hospitable place for all of these living organisms. This in turn gives our immune system that needed time to switch over, turn on, and get onto the scene and things not be completely out of hand. But fevers are also good for things beyond just crowd control. Some of our immune cells, such as T cells, roam our bodies in a standby state. They aren't doing anything, but they're poised. However, when these cells recognize that there's an increase in body temperature, it flips internal switches in the cell that allow them to activate and be prepared to respond rapidly. So a fever is clearly a pretty important part of an immune response. So much that even the muscles in our body try to help to produce heat by shaking slightly. And we experience this as the chills. However, we can't just crank the heat all the way. That would be kind of bad. Regulating this heat is one of the functions of vasodilation. Usually, our blood vessels maintain a very specific diameter and thickness and overall size to regulate how much blood is able to leave the vessels to get into the tissues to provide oxygen to all of the cells. This also helps to keep all of the other cells and proteins and molecules that travel through the blood in the vessels so that they don't interact with any cells that they shouldn't be interacting with. Now, one of the ways that these vessels are able to maintain this precise level of containment is by the arrangement of the cells in the vessel. Usually the cells sit rather tightly together and they don't allow things like cells to leak through very easily. However, when the molecules from this reaction are received by the cells in these vessels, they start to rearrange. And by this, I mean they lose that very tight arrangement and the vessels expand, but also, as you can see, become a little bit leakier. This looser arrangement, this leakier vessel, is going to allow more fluid and, as we'll see, more cells to slip between these cells out of the vessel and into the surrounding tissue, predominantly in the area where this reaction is taking place. However, thinking about heat and getting rid of excess heat, vasodilation puts these vessels and its heat-carrying fluid closer to the surface of the skin where the heat can dissipate more easily. We usually observe this as some redness underneath the skin. And vasodilation, again, isn't just helping us from suffering from heat stroke. These vessels are like the highway system of our immune system. When the vessels expand, it's like getting an extra lane of traffic on the road, while the loosening of these cells is like a whole lot of exit ramps that the immune cells can use to escape the vessels and, again, get into the tissue where all of this action is happening. So we just saw how vasodilation, in addition to helping us not die of heat stroke, also helps our immune cells travel through the body faster and then also get out of the vessels into wherever the action is happening. But how do these cells know where to go? That's the job of recruitment. These molecules that were produced by this first immune cell that recognized that this spike protein doesn't belong have traveled through the blood vessels and acted like a breadcrumb trail for these immune cells to follow so that they can get to the correct destination. However, like we hinted at with vasodilation, these leaky vessels aren't just allowing these immune cells to slip through. They're also allowing extra fluid to leak into this space. Now, while of course getting immune cells into this area where there's some sort of outside threat shown up and the extra fluid is helping to dissipate heat so that we aren't overheating, let's think for a minute what a typical organ looks like. You could imagine that it's similar to a puzzle where everything has its place. The cells fit together and they're arranged a particular way because there's a finite amount of space in, well, every part of our body. Now imagine introducing a whole lot of extra stuff. Yeah, you're going to end up pushing things out of the way. This pushing out of the way is what we see as swelling. This swelling is going to be most extreme where all of this activity is going on. Now, while inconvenient on its own, as the swelling increases, eventually nerve cells in the area get pushed against such that they create sensations of pain. So this is the reason why in these swollen areas they can sometimes feel tender or even very painful. Keep in mind, while this is going to be most extreme wherever all of this activity is going on, these molecules are circulating our body and have some mild effect, probably systemically. So when we experience achiness, then we could probably attribute it to some low-grade swelling throughout our body. So, we've scratched the surface of an immune response, and along the way, we've come across almost every single one of our common side effects to these vaccines. These side effects are really just macroscopic experiences of microscopic actions. And remember, this was only stage 1, minutes after the initiation of the immune response. Later stages are going to involve more cells, including the B cells that are going to produce the antibodies. It's going to involve going to farther sites like lymph nodes to generate long-term and memory responses. However, getting to this point is going to take some time. On average, probably about 14 days or 2 weeks for profound antibody responses to be developed. It's this lag, which is the reason why we've seen these couple of instances where individuals developed COVID disease shortly after receiving the vaccine itself. They were likely already infected before they got the shot, or they were exposed shortly thereafter. The immune system is pretty incredible, but it does take time to work. Now we've focused on the common side effects, which really are the immune system activating the way that we want it to produce protective immunity. But you might be concerned about these rare reports of adverse reaction. Let's think about immune systems as vehicles for a moment. Vehicles have their differences. Some vehicles are able to sip gas coasting through town, others can carry very heavy equipment, and others are the ideal adventure recreational vehicle to go over ridges and across rivers. But there are similarities between these vehicles. They all have tires, steering wheels, and they have a gear shift to allow you to put it in either park, reverse, drive, or neutral. Similarly, most of us have immune systems that have more or less the same components. T cells, B cells, macrophages, these are all similar. However, like our vehicles, the immune system of each individual person may be slightly different. One person may experience allergies to pollen, another person may not have allergies, but may be susceptible to strep throat. But overall, our immune systems respond similarly enough that something like a vaccine can be produced for the population at large, much like how, even given the difference in automobiles and vehicles, we can all follow the same traffic laws and use the same roadways. However, then we get into this classification of vehicles called hypercars. Hypercars are optimized for performance. However, given their high upfront initial cost as well as their high cost of maintenance, you don't frequently see hypercars zooming along on the highway in rush hour. We can compare this to those individuals who may experience a severe allergic or adverse event because their immune systems respond so much more robustly, aggressively, intensely than do most of the populations. While we can make a vaccine that is going to more or less induce the same kind of immune response in most people, with the variability being one person may run a low-grade fever, another person may only experience some tenderness in their arm for a day, individuals with these highly sensitive, reactive, and allergic immune systems are exceptions to these norms. So I hope that this has helped us feel a little bit more comfortable and make sense of some really complicated science. The idea of side effects can initially seem scary, but it's important to keep in mind that in these cases, the side effects that we're talking about are really our immune system responding to these vaccines so that they can actually produce the immune response, the protection that we are using them for. It's also important to point out that this vaccine schedule is very important. Our immune system takes time to build this response. You would not rush your construction company to build your house because that could lead you with a very poor foundation and you probably wouldn't have a house for very long. So, let's allow our immune system the time that it needs to make the protection that we are relying on it. These vaccines are going to be an important and even crucial tool to help us get rid of this virus and get back to life as normal. However, we don't need to be making it harder on everyone else as well as on these vaccines to do this, but make it easier for the virus. So let's continue to follow public health guidelines, wear our mask, avoid gatherings, wash our hands so that we can stop giving this virus new bodies to survive in. When this pandemic ends depends on all of us and all of our actions. So let's end this thing.